A glimpse into the future. Into the future. We're going to talk about equations, specifically one variable linear equations, which are really the simplest kind of equation that you can actually start to solve. And we actually don't go much further down the rabbit hole than that, which is good. We don't quite get into things like quadratic equations, the quadratic formula, fun business like that you'd see in a normal algebra class. Because again, this isn't a normal algebra class. It's a little bit of a weird hybrid course designed to prepare you for Math 1332, and so that you can pass that. And so we just kind of cover a number of topics, and this is among them. A linear equation in one variable x. So here, this definition we're about to make, our only variable, true variable, is going to be x. A and B in this are meant to represent numbers that you might actually encounter in an actual equation that you would have to solve. So just keep that in mind, bear that in mind while we work these. A linear equation in one variable x is an equation that can be written in the form ax plus b equals big fat stinking 0. A and b are real numbers where a cannot equal 0. That's going to be kind of our most basic way of thinking about it. Now, what we're going to end up doing, solving an equation in x, involves determining all values of your variable x that result in a true statement when substituted into the equation. Such values are called solutions. Sometimes they're called roots. Now, my family is from the Midwest. I was born and raised in the great state of Texas. But my family was born and raised in the Midwest, Illinois and Nebraska and Iowa. And they pronounce the word root as root. They say, you can take the square root of that. And they pronounce, my dad will still say the word wash. He'll say wash. He'll say, wash the laundry. I don't know. So you might hear me say root. That's when I'm really focusing on trying to pronounce it correctly. But sometimes my pseudo Midwest upbringing might just have me say root. And you know what? There's nothing I'm going to do about that. If you hear me say root, you're just going to have to live with it. Okay? No, I'm just kidding. You can say, please, Mr. Gunther, never utter that horrible word or pronunciation ever again. I will never forgive you. So you're free to say that to me at any time. But please don't, because my self-esteem is very fragile right now. It's not. Anyways, so we're solving an equation. Ultimately, what we're going to do, we're going to use addition and multiplication properties of equality. What that means is I can add or subtract a number as long as I do it to both sides of an equation, as long as I'm fair about it. I can multiply or divide both sides by a number, except for 0. You shouldn't do that with 0. Any other number you can do. With that in mind, we can use that in order to isolate the variable x. So let's just dive on in to these different properties. The addition property of equality says, hey, you can add a number to both sides of an equation. And you can even add a negative number, aka you can subtract a number from both sides of an equation if that is what serves your particular purpose. If that gets you what you need, then I say Godspeed. So let's look at an example. You got your variable x. You got minus 17 equals, how about negative 12? X minus 17 equals negative 12. Let me make sure no one's trying to get in the room. Okay. Well, here's a couple things I could do. Here's something I could do. hey, I can add any number I want to both sides of the equation, right? Anything I want, as long as I do it fairly to both sides. So here's what I'm going to do. I'm going to add 30. I'm going to add 30 to both sides. Well, negative 17 plus 30 ends up becoming positive 13 on the left-hand side. Negative 12 plus 30 ends up being positive 18. Everyone say yay. Everyone say yay. Yay. Everyone say yay with a little enthusiasm. Yay. If you're out there in the Zoomosphere, I hope you're doing this at home. I hope you're sitting in your living room or wherever you're doing it. And I hope people hear you say yay, and I hope they wonder to themselves, wow, that math class must be a lot of fun. It sounds like it because you're excited about being in your math class. And it's very true. Okay, not yay in this case, because did I really help myself solve this thing? No, I'm still in a pickle, aren't I? So I can add whatever number I want to both sides. That was the point of this whole thing. What should I have added? Exactly. In reality, I should have added 17. So yeah, you can add whatever you want. So the whole point of it is to add something that's smart. In this case, if I would have actually just added 17, that's going to isolate x. That's going to get x by itself. X is one of those forever alones who cries on the internet about how nobody loves them or something. And while that might be a sad situation, that is what X is consigned to, you don't have to be that way. You're only as alone as you want to be. I believe that. Unless you live in like, Alaska or something, like in the wilderness, but then you probably chose to live out there. I don't imagine you just woke up there by chance one day. Anyways, so X wants to be all by itself in this cruel, lonesome world. If I was by myself for a week, that would be 1 week straight of Minecraft, nonstop Minecraft. And Hot Pockets, would I be eating Hot Pockets and Taco Bell and not Pizza Hut anymore? It's too greasy. Like, I can't eat it. It's just, it gives me like a headache when I eat it. It makes me throw up sometimes. We get X all by itself. We get X equals 5 as our solution, meaning if I were to go all the way back in time and take this and plug it in for X here, well, you'd end up with the equation 5 minus 17 equals negative 12. 5 minus 17, though, really does equal negative 12. So you end up with a true statement. Whoa. You end up with a true statement here. Thus, X equals 5 really was a solution to this equation, to your original equation. That's what that means. That's all you're doing when you're solving. You're finding a value that can be substituted or values. Some equations have multiple solutions. So you're finding a value or values that can be subbed in and boom, you get a true statement. If you get a false statement from plugging in a number, that must not be a solution by definition. So good stuff to know. We can solve equations just by randomly guessing. I can randomly toss numbers in for X and hope something shakes loose. But that's a really, 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 really awful method for most types of equations to solve. Guessing and checking, there are some times when guessing and checking is appropriate, but solving equations is not one of those times. Doesn't make sense. How many numbers are there? How many real numbers are there that you could guess? Well, how many grains of sand are there on the beach? How many stars are there in the sky? I don't know. It could actually, in fact, be infinity. There's an infinite amount of numbers you could guess. So clearly guessing and checking is not a good idea. You're very unlikely to randomly guess the correct answer. The multiplication property of equality. This is a really wordy way here. The same non-zero real number may multiply both sides of an equation without changing the equation's solution set. That really means is I can, just like I can add or subtract a number from both sides, I can multiply or divide both sides of an equation by a number as long as it's the same number and as long as it's not zero. Don't multiply both sides by 0. You can't even divide by 0 if you had wanted to. So avoid 0. Avoid 0. Imagine you have 6x equals negative 24. It's always creepy that the hall lights turn off. There's a sensor. Like I see it turn off and I'm like, oh, is it real dark outside? Is there an eclipse? Is it the end of the world? Yeah, it is not that. It is not the end of the world. It's just there's a sensor in the hallway lights. That's it. Anyways, 6x equals negative 24. Could I divide both sides of this by 20 million if I wanted to? I guess. Could I multiply both sides of it by 15? Sure, have at you. And you're not going to change whatever the solution truly is. What is the right thing to do here, though? Divide both sides by positive 6. Exactly. Here, the x is being attacked, if you will, by the 6, but not on Titan. So we're going to do here. We're going to do here. We're going to end up with x by itself on the left. On the right, negative 24 divided by 6 will give you what? Negative 4, exactly. It's got to be negative because it's a negative divided by a positive. And then just 24 divided by 6. Hey, if you remember that 12 by 12 multiplication table, which I don't force you to memorize, but I tell you, look, take 30 minutes to memorize that thing and you will save yourself hours later on. Isn't that a good investment of time? Absolutely, that's a good investment of time. You'll get x equals negative 4. Again, you can check if that is a solution. And I say a solution, not the solution, because we don't know just yet that all linear one variable equations will only have one single solution. Again, whatever, if you had a quadratic, meaning you had x squared involved and a few other rules, there could be up to 2 solutions. If you had a 5th degree polynomial in x to the 5th and some other business, and that was your highest power, you could have up to 5 different solutions. So for now, what we're going to say is that, look, if it's not written otherwise, a linear equation, the power on x is 1. The implied power on x is the first power. That's what makes it linear, and that's why we're going to end up with only one possible solution. No more, and we'll also we will understand no less either. So interesting stuff. Now the real deal, combining these rules. Let's think of an interesting one. How about that? 3x minus 7 equals negative 10. Here's where we're going to combine the rules. We want x by itself, don't we? That's the goal. X says, you know what? I had a long week. I just want to, I need 24 straight hours of Minecraft by myself. I'm going to get one of those full throttle blue agave beverages. Full throttle is the best energy drink because it tastes good. It tastes like a soda I would just want to drink. And it's chock full of caffeine, and I need caffeine to live. If I didn't have caffeine, I probably wouldn't be here right now. And I don't mean that I'd be passed away. I just mean that I'd be in bed. I'd never be able to get out of bed. And that might be a sad story, but you know what? It's also not true. I would still suck it up. I would just be a lot less happy. Anyways, caffeine's great. Full throttle blue agave is great. Taco Bell is great. 3x minus 7 equals negative 10 is also pretty gosh darn great, if you ask me. Because we're going to combine both rules now. Now, you're tempted to say, should I add the 7 first, or should I divide both sides by the 3 first? That's a great question. Yeah, we're going to add the 7. And you see how it just kind of clicks. The real reason is, technically, you could divide both sides by the 3 first. You're allowed to, but you would have to also divide the negative 7 by 3. You would also have to divide the negative 10 by 3. And that might get you into the realm of fractions before you necessarily have to. So if instead I choose to add 7 to both sides, like here, maybe I can avoid fractions, maybe not, but that's one less complication before I have to possibly bring fractions into the mix. So you're going to get 3x by itself. I added 7 here, so these cancel each other out. That's why I chose it. If I add 7 here on the right-hand side, what do I end up with? Negative 3. Very good. Now I've got 3x equals negative 3. What am I going to do? Yeah, yep. X equals negative 1. Once I perform the division, x equals negative 1. Now, it has been said in many philosophies, that one must check thyself before one finds thyself wrecked. In other words, we're going to check this answer by plugging it into the original equation. John Madden time. I'm going to take this negative 1. We're going to bring it all the way back up here into the original equation. 3 times negative 1 minus 7 equals negative 10. What I'm really doing is I'm asking the question, is this a true statement now? By substituting a negative 1 in for x. Well, 3 times negative 1 is negative 3 minus 7. Does that equal negative 10? Why, yes, it do. It do. Negative 3 minus 7 will give you the negative 10 your heart desires on both sides. So it works. It's a solution. That is a great way. If you solve an equation and it's a little bit nasty and you're not 100% sure you have the right answer, checking your final answer is a great way to determine if you've correctly found the solution. Now, of course, you could make mistakes just in checking it. You could make a math mistake or a multiplication mistake, but assuming you don't make mistakes, you really want to check your answer. You'll find also other mathematical equations, a lot of them involving square roots and logarithms, where you literally have to check your final answer. Because sometimes you're going to get the wrong final answer, even if you did everything right. So just going through this little table real quick. X minus 3 equals 8. You would add 3 to both sides. You're going to end up with x equals 11. X plus 7, not S club 7. X plus 7 equals negative 15. Well, I got to get rid of that 7 there, Pilgrim. It's being added, so I got to have to subtract it there. You're going to end up with x equals negative 22. 6x equals 30. Forget about it. Divide both sides by 6. You're going to end up with x equals 5. X divided by 5 equals 9. Now, since it's being divided by 5, what do I want to do to both sides? Exactly. I multiply by 5. Those 5s are going to cancel. You're going to end up with x equals 45 in that particular example. So good to know. Here's your little simple process for solving an equation. But again, you can sit down, you can memorize a bunch of rules, or you can start with your basic foundational building blocks of mathematics: addition, subtraction, multiplication, division. You introduce the idea of a variable in that you're doing mathematical operations on the variable. And now you can talk about, well, what do I got to do to isolate the variable? That's clearly my goal. And so you just use some math on both sides and your intuition kicks in. So yeah, you could memorize this 4-step process, but I don't think it's very helpful or valuable. But maybe if you're first learning it, perhaps it is. So you always have a bit of a 4-step process you could appeal to. Ooh, check this guy out. 2 times x minus 4 in parentheses. Let me go back. Minus 5x equals negative 5. All right, I want everybody here in the room and everybody in the Zoomosphere all at once to say, wait a minute, Josh, on the count of three. 3, 2, 1. Wait a minute, Josh. Or to put in the same level of enthusiasm. Wait a minute, Josh. No, I'm kidding. You guys are enthusiastic. How many of you like, Josh, it's 9:28 in the morning, which isn't horribly early. It's not like I'm saying 5:30 in the morning. I know people who have to wake up at 4 in the morning to, get up and get ready for work. And I don't envy those people because I do not operate on that schedule. But anyways, wait a minute, you might say to yourself, this doesn't look like an equation we've been solving. Well, you're right. But we've talked about the distributive property, if you remember. We called it the distributive property of multiplication over addition or something like that. We've talked about certain other properties and other things you might have to do. Combining like terms comes to mind. We still need to isolate x. That's our total goal here. So let's distribute this bad boy out. We might have to combine like terms after that, and then we can solve. That's okay. That's life. You're going to have to add some layers of complexity into things. So we'll use green. I'm going to have 2 times x, 2x, minus 2 times 4 is what? 8. I still have that minus 5x, and I still have that equals negative 5 on the right-hand side. What does it look like I should do next? Perfect, exactly right. If you can ever combine like terms, especially when you're solving an equation, almost always you should. You should almost always combine like terms, with rare exception. So notice I have a 2x and I'm subtracting off 5x here. So 2x minus 5x. Oh, that's going to give you negative 3x. There's still a minus 8 over there, Pilgrim. And still equal to a negative 5. And now this looks a bit more like the equations we've been solving up till now. It doesn't look so bad. What do I need to do? I got minus 8, so I need to add it to both sides. Negative 3x will equal, well, negative 5 plus 8 is positive 3. Then what do I got to do? Divide both sides by negative 3. What am I going to end up with? Very good. Bada bing, bada boom. So really, it's not so bad. It's not so bad when you break it down like that. Sure, I could go back into the original equation and plug in a negative 1 and make sure it works, make sure I really did find the right answer. You don't have to, but you could. In this case, we won't, but I would leave that to do for you to do. Any questions so far? Everything clicking? Everything good? We're good. How many of you've seen this before? Linear equation solving, one variable. All right, let's see if I can add some interesting wrinkles into it. It's called linear. It's called linear because if you were to make a graph out of equations that have this kind of structure, now we only have one variable, so it wouldn't quite be what you're thinking. But generally speaking, a graph of this, if you introduced a y variable, would create a line. It would be the graph of a line that has a slope and y-intercept. And so you see the word linear, the word line is embedded in there, and that's not a coincidence. So that's kind of where the word linear comes from. It requires your variable x to have a first power. It's not written because it doesn't have to be written. If you don't write a power on it, it's implied to have a power of 1. That's what makes it linear. If I tried to do something like this, the second I try to make it a second degree power, a third degree power, or a fifth degree power, you are out of linear territory. And then if you were to look at its graph, if you had a y variable involved, if you were to do that, it would no longer just be a straight line. It would no longer. Okay, I need to step out for 1 second. I'm a little bit under the weather. It's not COVID related one bit. So I will be right back. So you might have to do some exotic things to solve an equation. Ultimately, the goal is to isolate the variable. So if you use any of those properties we discussed, either today or last time, you'll be in the gold because those are mathematically sound. Blah, blah, blah. Okay, we'll look at an application. These graphs indicate that persons with a low sense of humor have higher levels of depression. So we can model them with certain formulas. These formulas involve fractions, but you can talk about the average level of depression in response to negative life events. I didn't know you could measure that with a number. Maybe the percent of people who indicate a certain level of depression after a negative life event. People who have a higher level of humor, they don't increase as much, meaning as they have a more and more negative life event, they don't feel it as much whenever it comes to their depression. So that is kind of interesting. We won't go into uber detail about this. It makes some sense. I mean, depression is definitely not something that's funny. What's really perhaps interesting, though, about these numbers is that it's hard to say whether you could just one day decide to have a higher sense of humor and suddenly it could wipe out your depression, right? That seems to be the implication behind this is, oh, well, just get yourself a better sense of humor. But the same issues or whatever they could be that cause you to have a low sense of humor may be the same things that has your depression. Or it could be even your depression, which is something that's natural to you and not your fault. It's a chemical imbalance in your brain, causes you in turn to have a lower sense of humor. So the implication of this graph is almost silly. Just watch more comedies and tell more jokes. That you probably would already want to do that naturally, So it's kind of a silly idea. We won't go into uber detail about it. Okay. Let's pause for realignment. We're going to talk about next, and I think we're going to end up doing a little freestyling with it. We're going to talk about proportions. We're going to see how linear equations can be used to solve equations involving proportion. Proportions allow us to break things down either into percents, and you could say this is, this part of a whole. That's okay. But basically, certain proportion equations will allow us the ability to solve certain things. We're going to have to use linear equations in order to solve certain types of proportion equations. Now, we know that you can express a proportion or you can express a part of a whole using a percent. So let's see, percent literally means per 100, not hundred. You see the word cent in there, you think of a century, which has 100 years. You think there's 100 cents in a dollar. So if you talk about percent, you're talking about how much of this is this per every 100 units possible. So for instance, if I say 0.3, normally, well, there's no percent in here, 0.3 apple pies, if you will. Well, when I use numbers this way, when I use numbers this way, no percent sign, it's just a regular decimal number. These are numbers measured per 1. Think about the difference. A percent is measured per 100. A regular old number is per 1. If you have 3 apples, if you have 7 apples, you have 7 for every 1 apple. You just have 7 apples. It's pretty straight up forward what you have there. You have 7 units of 1 apple. If I talk about parts of numbers like decimals, 0.3 apple pies, then for every 1 apple pie, I have 0.3 of it, which means I only have a fraction of it. I have a slice of it, perhaps a big healthy slice of an apple pie, more than a quarter of the pie. That's a pretty healthy slice. And so we just have to think about, okay, well, there's a difference between per every 1 and then per every 100. So there's a couple things you can do. If a percent means per 100, suddenly you can set up certain types of equations. Let's see an example of this. Let's say Cindy is entitled to 30% of Jan's earnings for the week. So Jan is someone who has a job, is making money. For some reason, Cindy is allowed 30% of it. Maybe they have an agreement worked out. Maybe Jan is paying Cindy back for something, a debt. So Cindy is entitled to 30% of Jan's earnings for the week. Jan makes $160 for the week. How much of that does Cindy get? Here's how we're going to do it. We're going to set up, at least initially, we can set up a proportion equation. Cindy gets 30 out of 100, 30%, 30 out of every 100. So Cindy gets 30 out of every 100 units, of Jan's money. We're going to set that equal to, we're going to call that X over 160, where X is the actual amount of money Jan will get from Cindy. Does it make sense why that proportion equation should be set up that way? 30 out of every 100 units is going to be equal to X out of every 160 units, where X is going to end up being what Cindy is going to get. So now let's solve this proportion equation. Let's bring it up over here. Well, we can use our linear equation solving. We can multiply both sides by 160. So over here on the left, on top, you could say that's 30 times 160 over 100 equals X. Now we need to do the 30 times 160. Then we just got to divide it by 100, and that will give you what X is going to be. So 160 times 30 we've got a 0 down here on bottom, so we're just going to add a 0 on the right, or you could just say the whole first row is going to be zeros. That's fine too. Then the second row, we start with a 0, and now we can do the 3. 3 times 0, 0. 3 times 6 is 18, so bring the 8 down, carry the 1. 3 times 1 is 3, plus 1 is 4. And now add things up, these zeros, 0 plus 8, 0 plus 4, You're going to end up with 4,800 divided by 100 equals x. Oops. Well, what is 4,800 divided by 100? Just 48, yeah. 4,800 divided by 100 is great. Dividing by 100 is pretty straightforward. You take your decimal point here, you move it twice over, and you've divided by 100. You're going to end up with x equals 48. Thus, for every $160 that Jan makes, Cindy gets 48 of it. That's what 30% of 160 is going to be here. So interesting to know. I'm sure this isn't going to go on forever. It's just until a debt is paid back, something like that. And that does it. I think this is a good stopping point today. Remember, everything technically we cover today won't be on the exam. The exam is going to cover previous knowledge, everything in the course up to and including section 6.1. Don't go anywhere yet. I got to take attendance. So we'll meet again tomorrow morning. It'll be just a normal class tomorrow morning. And then you'll have your exam on Thursday. We won't be meeting on Thursday as a result.